So I would like to start welcoming you all to the 37th webinar of the Graduate Program in Physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the cameras and microphones turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be asked using the chat, both in this virtual room and in the YouTube. Today, we have the great honor to listen to Professor Abhay Vasant Ashtekar, who is a member of the U.S. National Academy of Sciences and a winner of the Einstein Prize of the American Physical Society, given biannually for outstanding contributions to gravitational science. Professor Abhay Ashtekar is the director of the Institute for Gravitation and the Cosmos, Evan-Poole Professor of Physics and holder of the Eberly Chair at Penn State University in the United States of America. He received his PhD in physics from the University of Chicago in 1978. He has authored or co-authored around 300 scientific papers and written or co-edited 9 scientific books on general relativity, asymptotic structure of spacetime, gravitational waves in full nonlinear general relativity, atomic structure of spacetime geometry at the Planck scale, and the quantum nature of black holes and Big Bang. His reformulation of general relativity as a gauge theory has led to loop quantum gravity, an approach to the unification of general relativity and quantum physics that is now being pursued in dozens of research groups around the world. He has continued to play a seminal role in the development of this field, as well as its subfield called loop quantum cosmology. Professor Ashtekar is also one of the only 51 honorary fellows of the Indian Academy of Sciences, drawn from the community of scientists living outside of India. He was awarded the Senior Frauenprize by the Alexander von Humboldt Foundation. He held the Kramers Visiting Chair in Theoretical Physics at the University of Utrecht in Netherlands. He has been Senior Visiting Fellowship of the British Science and Engineering Research Council and the Sir C.V. Raman Chair of the Indian Academy of Science. He was awarded Doctor Rerum Naturalium Honoris Causa by the Friedrich Schiller Universität in Jena, Germany in 2005, and by the Université d'Aix-Marseille II in France in 2010. He is a past president of the International Society for General Relativity and Gravitation and the past chair of the Division of Gravitational Physics of the American Physical Society. Well, we are here today to listen to Professor Ashtekar, so that I won't take your time anymore with this introduction. Professor Abhay Ashtekar, thank you very much once again for having accepted our invitation. From this moment on, the audience is yours.
Thank you very much. It's a pleasure for me to join you. I think it is really wonderful that you have held so many of these seminars, and I know from the list of past speakers, there have been really scientists who have made big breakthroughs in our lifetime. So I'm glad that you have the young students are listening to these forefront results. My own topic today is purposely taken to be rather general, rather than providing you with some latest results that I have worked on. The goal is to provide a broad perspective of how the paradigm shifts occur in fundamental science. So that is the main idea. And because we are working in gravity and cosmology, the examples I'm going to take are from black holes, Big Bang, and gravitational waves. I know it's a very mixed audience, and that is why I thought such a broad topic would be of interest. And the point is the following, that for these paradigm shifts, there are some really counterintuitive things that have happened over the last century. And I think it is very good for both the junior people to know about them and keep them in mind, and also for senior people to sort of have this awareness while we do research at the forefront of science as to how these paradigm shifts occur and how they can change. And the main point is the following. There are three issues here that I would like to emphasize. First, what is now considered as common knowledge was not at all so a few decades ago. In fact, much of scientific community at the time was probably thinking in almost the opposite direction. Second, precisely because they are so startling at first, the dramatic paradigm shifts take decades to get settled and become the new common pool of knowledge, and therefore one needs a lot of patience. In the first one needs a lot of courage to sort of say swim against the direction in which one sees things moving. And the third is that factors driving or slowing the process are quite varied. It is not a matter of simple logical steps as is often made to appear in retrospect. And therefore one has to have this maturity to accept this. So this is the general idea, and I will illustrate these ideas through numerous examples. The first is general relativity itself. This is a rather broad introduction, and many of you know these things, but still there are some curious facts that illustrate what I was trying to say in the 3 points on the first slide. So general relativity, as you know, has to do with the nature of space, time, and gravity. Now, the most familiar ideas about space, time, and gravity really come from Newtonian paradigm, where space and time is an inert backdrop or an arena or stage in which things happen. The space-time is just sitting here and the planets move in the space-time. The space-time is unaffected, providing us a stage or arena. And the actors are these planets, the fields, the objects you see around you, and also you and me. So we all move in this space-time, which provides us an inner backdrop, according to Newtonian paradigm. And according to Newtonian paradigm, gravity is just a force between massive objects. And there is a universality, namely, all objects experience gravity in the same way. This is called the equivalence principle, as you know. Now, this paradigm reigned for over 200 years, but it was shattered by Einstein's theory of general relativity. In this theory, space and time fuse into a four-dimensional continuum. Its geometry is a physical, dynamical entity, just like matter. It can be acted upon and it reacts. It's no longer an inert backdrop or a stage. This is a radical shift in description of reality. Furthermore, this shift is absolutely essential when gravity is strong. And now there is even greater universality, as we will see in a minute. What happens is basically that gravity is no longer a force, but is absorbed into the very geometry of space and time. But how did this revolution occur? It occurred in these years, 1907 to 1915. As all of you know, in 1905, Einstein discovered special relativity, and space and time fused to form a four-dimensional continuum. And a major consequence of this was the famous equation E equal to mc squared. In Newtonian physics, energy and mass are entirely different objects, but here they are fused, which will reflect the fusing of space and time to form a four-dimensional continuum. But then 2 years later, Einstein was invited to write a review article on special relativity. And in this course, he realized the fundamental tension between special relativity and Newtonian gravity. Because in special relativity, there is no notion of absolute simultaneity. The events are simultaneous for one observer are not simultaneous for an observer who is moving uniformly with respect to the first one. But in Newtonian physics, the law of gravity, the force is equal to the product of masses divided by r squared, that law is really requires an absolute instantaneous notion of simultaneity. If I were to move an object right here, then Newtonian gravity says that the gravitational field changes absolutely everywhere at exactly the same time. And this is contrary to the lack of absolute simultaneity in special relativity. And therefore, Einstein realized that there is a tension. And then he started thinking that that means that perhaps one needs a new theory of space and time and gravitation. And Einstein was really way ahead of his time in thinking this, because in 1913, Einstein visited Planck in Zurich to attract him back to Germany. Einstein was at the École Polytechnique there, and he wanted to be attracted to ETH. He wanted to get him back to Germany. And he, after the administrative matters, Planck asked Einstein, so what was he working on now? So Einstein told him that he thinks that one needs a new theory of space-time and gravitation. And even Planck, the most senior and respected theoretical physics, insightful theoretical physics of the time, said, as an older friend, I must advise you against it. For in the first place, you will not succeed. And even if you do succeed, nobody will believe you. So this is a great lesson for particularly younger people, but also for older people, that in fact, Einstein was swimming entirely against the traditional wisdom. But Einstein, fortunately, persisted, and in 1915 found the final equations of general relativity. And so, as I said just a while ago, in general relativity, gravity fuses with the space-time geometry. Space-time is no longer an inert background or stage, but space-time is also an actor, just like matter, just like the planets, just like the fields, just like the tables and chairs, just like you and me. It can be acted upon and it reacts back. The gravitational field is encoded in the very geometry of space-time. So it's not a force, but it's really encoded as bending of space-time or curvature of space-time. And it is possible to absorb gravity into space-time geometry because gravity is omnipresent, it is present everywhere, and it is not discriminating. Equivalence principle, it acts the same way on everything else. And therefore, it could be absorbed into the space-time geometry, which is also all-pervading and sitting everywhere. In electromagnetic field, for example, the force is different between positive charges and negative charges. And it's not universal, so it could not be absorbed into the very geometry of the four-dimensional space-time. And similarly, gravity is everywhere. Everywhere in the universe, there will be gravity. Whereas in electromagnetism, you have laboratories which are shielded, in which there are no electromagnetic fields. So this universality and omnipresence of gravity is what enables one to absorb it in the very geometry of space and time. And then Einstein's equations say, basically, how matter curves space-time. And then equations of motion of matter tell us how space-time tells matter how to move, how space-time moves in a curved geometry. So for example, here is a depiction. Here is a central body like sun, and this is supposed to be the geometry of space. And the sun is bending the geometry. And the planet like Earth is trying to move. It is trying to move in a space, in a straight line, geodesic if you like. But from the perspective of Newtonian physics, which assumes that space-time is flat, it looks like its trajectory is actually bent. But the trajectory is just a geodesic in this bent rather than flat space-time. So this is the basic idea of general relativity. And then when Einstein sent his paper to the Prussian Academy, the next day, he wrote to Sommerfeld, who had the chair of theoretical physics in Munich, saying that during the last month, I experienced one of the most exciting and most exacting, most demanding times of my life. True enough, also one of the most successful. And then he goes on to explain that all this general relativity came from this desire to unify special relativity with Newtonian gravity, and therefore one obtained the grander theory from which special relativity and Newtonian gravity appear as special cases. But in general relativity, if you calculate the orbit of Mercury, then the orbit has a certain correction related to Newtonian gravity, and that resolves a long-standing discrepancy between Newtonian gravity and observations. Now, Einstein was not known to have such, rather excited expressions. He was very reserved, or his writings are very, very somber. And therefore, Sommerfeld was very surprised to receive such a letter. But then Einstein replied to him that, well, you'll be convinced of it when you actually study the relativity. But just like Sommerfeld was not convinced immediately, Other peoples were also not. And it took 4 years and the non-scientific world events for general relativity to be accepted as a revolutionary paradigm shift. And what was the non-scientific event? It was really a solar expedition that was led by Eddington, a British astronomer, who actually verified the bending of light from distant stars as they traverse towards us in the gravitational field of the sun. And this bending of light really coincided with Einstein's prediction of general relativity, which differed from Newtonian prediction by a factor of 2. And Einstein triumphed. And the reason why I say that this is really events which are not world events, which are non-scientific, is that Eddington was sent on this mission because during the World War, this is the First World War, Eddington was a Quaker, pacifist, did not want to fight. So according to British law, he would have gone to prison. And therefore, the Astronomer Royal actually arranged for Eddington on an official mission to go to the solar eclipse near Africa and really do this. So it's really a world event. And then when the news came in November 10, 1919, First World War was just over. And this was really a fantastic piece of news for people all over the world, because here was a theory by German scientists, and it was really verified by British astronomer, the enemies in the World War. And furthermore, it actually it actually toppled the Newtonian paradigm, which was, of course, the crown of British science. And so it showed that science really transcends the stupidity of war and violence and such thing of mankind and divisions that are caused by that. And that really was a very, very heartwarming event that really uplifted people. And therefore, this is the headlines in the New York Times. And it really became a worldwide news. And Einstein shot into fame, and general relativity became not understood, but at least accepted as a paradigm shift up here. And now general relativity is really beautiful. There are quotes, I won't go into great detail of all of them, one by Chandrasekhar, which compares general relativity with sculptures. And here is a sculpture of Michelangelo that Chandra refers to. Chandrasekhar was a preeminent astrophysicist of 20th century. And just as the greatest sculptures can be viewed, and indeed should be viewed from all distances, since new aspects of beauty are revealed at every scale, the same is true with general relativity, that you see new aspects of beauty as you study it at different levels. And this really is literally true. All my life, I've discovered new beauty, beautiful things. New beauty was revealed to me in general relativity as I studied more and more problems. And here is Hermann Weyl, a mathematician and a physicist, preeminent, and this really captures many people's sentiment. It is as if a wall that separated us from truth has collapsed. Gravity was in Newtonian theory of force, and space-time was inert, and they were combined, and everything just got unified. And therefore, a wall which separated us from truth has collapsed. Wider expanses and greater depths are now exposed to the searching eye of knowledge, regions of which we did not even have any faintest clue. We did not even have presentiment. So general relativity is very beautiful, but many of you may ask, okay, it's all beautiful, but why does it matter in practical terms? Well, the point is that it is inevitable. In fundamental laws of nature, always matter. For example, one thing that, well, general relativity to be relevant, conditions have to be like black holes and Big Bang and so on, very extreme. But in fact, they matter in our everyday life. It matters because all of us carry this gadget, the cell phone, and the cell phone tells us, for example, what our location is, guides us along a map, and that uses the global positioning satellite system. And the fact that space-time curvature changes the rate at which a clocks tick and changes the distances between clocks, that is really critical for the global positioning satellites to work accurately. If we ignore special and general relativity, then within 2 minutes, the localization errors will grow to about 23 meters, which is sort of roughly the slightly bigger than the runways, and therefore the airplanes will fail to land on runways. So these abstract ideas of curvature of space and time and so on actually matter. So this is the introduction of general relativity. And now I would like to go to the second part, which is warping of space and time and black holes. I chose to talk about this as the first example of the paradigm, of the application of general relativity in which paradigm shift occurred, because just recently, just 2020, Nobel Prize was given for black holes. These are regions of space and time from which even light cannot escape. Here are two illustrations. Here is an artist's depiction of a star which is really accreting matter onto a central black hole and producing the jet up here. And here is so these jets have been observed. And here are the various events from the LIGO gravitational wave observatories, laser interferometric gravitational wave observatories. And these events have told us that there are many, many binary black holes in the universe. And therefore, today, black holes are widely recognized as engines that drive the most energetic phenomena of astrophysics. But it would come as a surprise to younger people that this was not always so. Again, the subject has a curious history. As you now see, that there was a Nobel Prize announcement of October 2020 was for theoretical foundation for black holes and supermassive compact object at the galactic center, given 1/2 to Roger Penrose for the discovery that black hole formation is a robust prediction of general relativity, theoretical side, and here on the observational side of what happened, the observations concerning the supermassive compact object in our galaxy. So here is a picture of a galaxy, and the supermassive compact object is a center. Here are little arrows that you see up here. It is over here. So it has about 4.3 million solar masses. It's called Sagittarius A star, SGR star. At the closest approach, S2 is about 1400 Schwarzschild radii, so a few light hours away. So here is a Sagittarius, and as the closest approach of a star, it is about a few light years away from the black hole horizon, from the surface of the black hole up here. And now the reason, of course, this object is black. There is no light coming from it, so we do not know directly that it exists. The way we know it exists is by observing very carefully orbits of stars around it. Right? So people observe stars around it, and looking at these orbits of stars, you conclude that there must be a central object of about 4.3 billion solar masses, even we do not see this object itself. By its effect on stars, we can deduce its inference, its existence. And this is exactly what was done by astronomers, Genzel and Gens and their groups, that they observed this star going around between 1992 to 2018, so long period up here, and they actually found that it was exactly in agreement with the central massive object up here, which is dark. Now, amazingly, this prediction that one could actually, that there might be such objects whose existence could be deduced from the orbits, was made over 230 years ago. And in fact, it was based on Newtonian theory of gravity. And this was a paper by John Mitchell in 1784. And he said, if there should exist in nature any such bodies which are dark, we would have no information from sight. Yet, if any other luminous bodies should happen to revolve around them, we might still perhaps, from the motion of these revolving bodies, infer the existence of the central one. So this is exactly what Genzel and Gens did. They actually observed these orbits, and from there they deduced the existence of this black hole. So it is really a long time ago, and there was also the books of Laplace on celestial mechanics, which had a similar treatise, which came just a little bit later, but very much more detailed. So you might think that, oh, Newtonian theory, there are black holes, we don't really need general relativity. And particularly this example of black holes is often given in classes and so on, saying that you can deduce from Newtonian gravity that black holes exist. But this is wrong. And I want to emphasize this, that the reasoning behind this fascinating conclusion that there are black holes in Newtonian theory is conceptually flawed. Because speeds of light, all speeds are relative in Newtonian physics, and therefore speed of light is also relative in Newtonian physics. So therefore, as a result, for example, if you had a central object, like in this picture, if you had a central object like in this picture up here, one could shine light on it, and then just by conservation of energy, as it is conservation of momentum, actually as it is falling towards the object, the speed of this light ray would grow and grow and grow, and it would really can exceed the escape velocity of light which is fixed in the rest frame of this object, which is fixed. So as the light ray is falling, its velocity will grow and will exceed the escape velocity, and then by conservation of momentum, it will be reflected, and therefore it will be seen. So it is not really true that there are black holes in Newtonian physics. In fact, there are no black holes in Newtonian physics if you apply Newtonian physics in a consistent manner. We need both an absolute speed of light and gravity. And absolute speed of light comes from place of relativity. And if we combine that with gravity, as we saw, we have general relativity. We do need general relativity to have a consistent notion of a conceptually consistent notion of a black hole. And general relativity, here is a diagram which was drawn by Roger Penrose and used by the Nobel Committee. Here, time is running upwards, and horizontal direction, if you like, we can only draw 2 here, but there are 3 in reality. That is space. And here is a world tube of a star. So here is the surface of a star that collapses. If it undergoes a collapse, this is what happens. And then what happens is that there's a region around here from which light cannot escape. So what happens is that geometry is bent. Out up here, geometry is like Minkowski space, light cones are upright. As you come closer to the star, light cones start tilting, and inside this region, the future light cone is all inward pointing. Here, the future light rays can go out, can fall into the black hole, but it can also go out to infinity. Whereas here, all light rays that are emitted are trapped, they remain in this region. So there can be these trapped regions in space-time, and these are the black holes of general relativity. Now, the curious history of black holes is that the simplest black hole solution was discovered by Schwarzschild while he was serving on the front, in the German front, during the World War I. But a clear black hole interpretation had to await several decades, both because leading researchers did not understand the geometry and the interplay between geometry and physics very well. Initially, there was a great confusion about what we now call the event horizon, the surface up here of the black hole, such that it traps light rays, that's the event horizon. And there was a great confusion. Initially, people thought that this was a singularity. It took a long time to realize that there is nothing strange about it. This is perfectly fine object up here. The singularity is in the center of the black hole, but here everything is perfectly fine. So it took a long time to understand this causal structure, the idea that there's a trap region, and so on. And there are pioneering works by Lemaitre in Belgium and Finkelstein in the United States, and they showed that in fact there is that the geometry here is not singular, is not divergent, everything is completely regular here, and that is not the black hole singularity, but rather inside you have a region in which light is trapped, and that is the black hole region. Now the point was that Chandrasekhar already between 1931 and 1935 discussed that the fate of heavy stars. If you have very heavy star, after they burn out their nuclear fuel, they would collapse, but because of the Fermi degeneracy pressure, if you have a lot of fermions, you cannot put them in the same state, and therefore there is a certain force that comes up that actually prevents the collapse. But if the star is sufficiently heavy, then this Fermi degeneracy pressure is not sufficient, and the star just collapses, and therefore it would form a black hole. And in 1939, Oppenheimer-Schneider really worked out in detail a solution of Einstein's equation, which was spherically symmetric, and showed that a spherically symmetric solution with just dust actually can undergo a gravitational collapse to form a black hole, and really obtaining exactly this kind of causal picture and developing horizon, etc. They really showed this in detail, that this can actually happen. So this idea from astrophysics, the fate of heavy star, and this idea from mathematical physics, solution of Einstein's equation, established the existence of black hole. But there was a general reluctance in accepting the idea that stars more massive than the Chandrasekhar limit have no equilibrium configuration once they exhaust their nuclear fuel. This was the mainstream belief, that astronomers preferred a serene and calm universe, not a violent one in which the stars undergo this collapse, a violent collapse, and in a matter of milliseconds, it collapses and forms a black hole. And there was another quirk of history. Although this paper appeared and showed a completely in detail that spherical stars can collapse if they're sufficiently massive, they'll collapse and form a black hole. Astronomers, this particular paper was ignored because the same day that this paper appeared in Physical Review, Hitler invaded Poland, and it was also the same day in which Oppenheimer and Schneider, in which Bohr and Wheeler wrote a paper on nuclear fission. So the whole world was really focused on this Second World War, nuclear fission, bombs, and so on and so forth. So this seminal discovery was not really registered, neither in astronomers who preferred a serene universe, not with physicists. It took a long time. There was a reluctance in accepting the existence of the black hole. The same Eddington, who played a seminal role in establishing general relativity, did not like black holes at all, and made remarks which seem extremely strange in retrospect, but made them in some meetings of the Royal Society, that various accidents may intervene to save the star, but I want to have more protection than that. I think there should be a law of nature that to prevent the star from behaving in this absurd way, collapsing to form a black hole. He didn't want to accept that black holes could exist. And interestingly, Einstein himself published a paper in 1939, the same, just a few weeks before before Oppenheimer-Schneider paper appeared, saying that the stars would not collapse to form a black hole. The calculation is correct, but the approximation he made is wrong. He assumed that if a collapse occurred, it would be adiabatic, it would be very slow. In fact, what happens in the Oppenheimer-Schneider collapse is that it's far from being adiabatic. It happens in a matter of milliseconds, and therefore these approximations fail, and the real solution is really a black hole solution. So all this was going on for a very long time, as you can see, and it is only in 1965 that Penrose showed, without any symmetry assumptions, because Oppenheimer-Schneider paper assumed spherical symmetry, and so a lot of people thought it was an artifact of the symmetry assumption, and generic stars are not exactly spherical symmetric, and therefore they would not collapse. But Penrose's 65 paper showed that generically, if one accepts general relativity and physically available matter satisfying energy conditions, then gravitational collapse will lead to a space-time singularity. And in that, Raychaudhuri equation plays an important role, just for those who know. And therefore, here we come to the Nobel announcement, actually, for the discovery of black hole formation is a robust prediction of general theory of relativity. So this is now, black holes are routinely invoked as engines that drive the most energetic explosions in the universe. But my main message to you is that it was a long winding path, as we see here, that there was great reluctance. The majority of physicists or astronomers were thinking in the opposite direction, and it required great courage on the part of these people like Chandrasekhar, Oppenheimer-Schneider, and Penrose, to swim against that current. And the current was driven by very powerful, very eminent, very thoughtful, deep people, and yet they were wrong. And this is what happened in this particular episode up here. So this is my first application, and now it is about 2:43. So I've spoken for about half an hour. And so what I would like to ask is, maybe if there are some questions on this part, let me take them. And if there are not many questions, then I can go to the modern cosmology. I don't mind skipping part of my presentation if there are a lot of questions. So if there's any questions at all on general relativity of black holes, you can raise them now.
Professor, I think people want to hear more from you at this moment.
All right. Then I can go to the modern cosmology. And here is a second example of the paradigm shift of Big Bang. All the students sort of almost are born to think that, well, I mean, everybody knew that there was a Big Bang. It was something common sense. Of course, the universe began with a Big Bang. Well, it was not at all so. And this is what I want to say. Today, we all believe that what we do know is that if you use Einstein's equation and add to it an observational fact that homogeneous, that space-time, that the observed universe is homogeneous and isotropic on all large scale. Homogeneous means there is no preferred place in the universe on a sufficiently large scale. And isotropy means that there is no preferred direction, again, on a sufficiently large scale. This is the largest, grandest realization of the Copernicus principle: no preferred place, no preferred direction. If we add this to Einstein's equation, then it says that geometry must be dynamical. It is related to dynamical, so changing in time, and it is related to matter via Einstein's equation. The geometry of universe is still changing in time, and the standard picture is that the universe began with a primordial explosion about 13.8 billion years ago. And this is a big paradigm shift because it took a long time to accept this conclusion. Again, this may come as a surprise to many people, but the issue of beginning at the Big Bang or not the Big Bang has, again, a very curious history. Einstein found equations of general relativity in 1915, and in 1917, Einstein and de Sitter found some solutions which they thought represented the large-scale structure of the universe. I've drawn here the de Sitter universe, which is the hyperboloid, like that. But the point is that an Einstein's equation has the same topology: three-dimensional sphere representing space and one-dimensional time. So this is compact, and here it is, time is fluent. So this was the universe, and there is no singularity. The universe is eternal. There is no beginning or end. In Einstein's universe, which is static, the matter and gravitational force, so to say, the cosmological constant, the repulsive force due to cosmological constant, and the attractive force due to gravity on matter balance each other and make a static universe. In the de Sitter universe, there is no matter at all, and again, it is a universe which is in which there is no beginning nor end. The topology is same, the solutions are different, but in both cases, there is no beginning or no end, and therefore there is no singularity. But between 1912 and 24, Friedman, and independently, between 1926 and 65, Lemaitre worked on the early universe, made many seminal contributions up here. But Friedman discovered solutions of Einstein's equation in which the universe is expanding. Again, the time is running in this way, and this is supposed to be the space at one instant of time. And as you can see, the space is expanding, just like here, the space is expanding up here. So here, the space is expanding, except that if you go back in time, then the volume here goes to zero, the curvature blows up, and therefore, in this picture, the universe really began with a singularity or a Big Bang. This is where the space-time is all smooth and nice, but as you go back in time, the space-time continuum tears. It is torn apart, and classical physics just stops. And this is the Big Bang. But this picture, for majority of the time, for many, more than a decade after this, most of the leading scientists continue to believe in this kind of a picture: no beginning and no end. In fact, in 1930, in a Royal Society meeting, Eddington sort of only considered these two models and then pointed out that in Einstein universe is static, there is no motion in it. In de Sitter universe, there is motion, it is first contracting and then expanding, but there is no matter, and neither of them are physically right, And so we need a dynamical universe with matter. Are there some solutions like that? And then Lemaitre, who had spent a few months in Cambridge with Eddington, wrote to him and said that, in fact, he had found such a solution many years ago, and this solution actually existed. To his credit, Eddington immediately accepted the solution of Lemaitre, and also therefore of Friedman, same solution, and was willing to accept that the universe really began with a Big Bang. But the conclusive thing came from Hubble's discovery that the universe is actually expanding, and this occurred here, and this is what made Einstein change his mind. And therefore, the Lemaitre seminal role really was in between 1929 to 1931, before, in fact, the Hubble's discovery actually came. A few months before that, Lemaitre had worked out how the expansion of the universe would be seen in observations, and that is what Hubble actually discovered. In his papers, Hubble only talked about redshifts and observations and left it to theorists to understand what this really means in terms of the universe, and it was really Lemaitre who had pointed out before what it means. There's also another interesting episode of Lemaitre, just as a side remark, that in 1951, George Gamow, as we'll see in a minute, actually pointed out that nuclear abundances, observed nuclear abundances in the universe, implied that there must have been a hot phase in the early universe, which was really the Big Bang. And he wrote to Pope Pius saying that there is a Big Bang, and therefore there's a finite beginning, and therefore religion and science are coming together. Pope Pius XII was excited and made a big announcement in a scientific meeting that he inaugurated. But Lemaitre went to the Pope and told him that no, we should keep the science, and convinced him that we should keep science and religion separate, and we should not mix them up. So Lemaitre had a lesson for Pope. He also had a lesson for Einstein, that the universe was actually expanding. He had another lesson for Einstein, which said that whether there is a cosmological constant or not is an observational question, and it's not an aesthetic one. We should not dismiss it on the basis of aesthetics. And so Lemaitre, I admire him because he had the courage to correct both Einstein and the Pope. But still, philosophical and aesthetic preferences existed. There was a program in Soviet Union by Lifshitz, of Landau and Lifshitz, Kalatnikov, in the late 50s, which somehow tried to show that the Big Bang singularity of this kind was exceptional. It was an artifact of symmetries, and in a generic solution of Einstein's equation would be non-singular. And there was a steady state universe idea, which was against the Big Bang, in which the universe is again in a steady state. There is no large-scale dynamics, proposed particularly by Hoyle, but Narlikar, Bondi, Gold, Sciama. And all these things basically supported a universe without a Big Bang. The paradigm shift occurred because of nuclear synthesis that I just mentioned. George Gamow, with his younger collaborators, sort of did a very detailed analysis and showed that although most of the heavy elements in the universe are probably cooked in the stars, the lighter elements could not have been, particularly helium and lithium, could not have been cooked in the stars. There could not be, not all of them could have been cooked in the star. The abundance was much larger, and there had to be a mechanism in the very, very early epoch, before the stars even formed, which actually created the lithium and the helium that we observed the universe. And therefore, in the very early epoch, the universe, there must have been an epoch in which the universe was very hot, and that means that perhaps there was a Big Bang and not a steady state universe. And then there was also the cosmic microwave background, which was observed by this called CMB, and it was really understood much more by Dickey, Peebles, Roll, and Wilkinson, Dickey and his younger collaborators up here. And this really is a relic. If you have a Big Bang model, then the universe cools before it reaches. So in the beginning, it's very hot, it cools. When it's very hot, the photons and matter cannot decouple. It's just too hot. The photons get scattering. Atoms cannot form. When the universe is sufficiently cool enough, then the kinetic energy due to the temperature can be less for electrons, would be less than the binding energy needed to form hydrogen atom, and then the atomic atoms form, and then the photons can decouple, and these photons which are decoupled can propagate freely, and therefore they should be around today, and this is the microwave background, and this microwave background was actually observed. So here is a picture of the universe. Time is again running up. The horizontal axis or space axis up here. Here is the formation of the C and D. This is the early universe. Before here, the photons were bouncing around. They could not escape because they were always interacting with matter. Here, atoms form, and then the photons could actually escape. The universe is cool enough to leave the atoms in a bound state, and the photons can escape. And they escape out here, and then we're seeing it today. And so there is a spectacular success over the past 2 decades. There's a powerful interplay between theory and high precision observations, especially through space missions. The first mission was COBE in 1989. Then there was WMAP in 2001. And finally, there was a Planck satellite launched in 2009. And then final data release came from 2018. And all of them are consistent with this universe, which was very hot in the beginning and is very well modeled by the Friedman, Lemaitre, Robertson-Walker universe, their solution that they had found. And in that sense, then, in classical relativity, there is actually a Big Bang. So what these observatories, these satellites actually observed was that this cosmic microwave background has a very beautiful, exactly thermal spectrum, extremely small errors, which are in this red crosses up here, and it really lies on the theoretical prediction. When the universe was 380,000 years ago, when the universe was 380,000 years young, the universe was extremely homogeneous, as Lemaitre had envisaged, and it was a perfect black body with temperature that today is about 2.3 degrees Kelvin. As the universe expands, the temperature cools. Today, it is about 2073 degrees Kelvin. But there are tiny inhomogeneities. So these are almost homogeneous, but they are very tiny inhomogeneities which were observed, which are 1 part in 100,000. And these inhomogeneities grow. Because if there's a little more matter, like in this blue region, if there is a little more matter, then it attracts by gravity even more matter. And if there is less matter in some region up here, then the matter in this region where there's less matter up here is actually taken away by gravitational pull to regions where there is more matter, where there's stronger gravity. And therefore structure is formed, and the detailed numerical simulations one can do about the evolution of the structure show that this little inhomogeneities that we have, they grow into what we today see as a large-scale structure of the universe. And this is really triumph of general relativity, because what we see here is when the universe was 380,000 years young. What we see today is when the universe is about 13.8 billion years. If you take the ratio between these two numbers, it is the same as 1 day to 100 years. So in human terms, this is like the snapshot of a baby 1 day after birth, 1 day, and 100 years, which is 13.8 billion years here. And then today we know enough physics and astrophysics to be able to predict what this baby would look like 100 years later. Imagine how much work, how much advances there would have to occur in physiology, biology, biochemistry, chemistry, in order to be able to predict what a human being would look like 100 years later from the picture of the human baby, which is only 1 day old. And therefore, we should all be very, very happy and very, very proud of the cumulative progress that mankind has made in physics, that we can actually predict what the universe should look like 13.8 billion years later, starting from what it was 380,000 years earlier. There are also issues that I wanted to talk about, which has to do with what about the origin of these inhomogeneities themselves? Where did these come from? So this is one of the things that we would like to talk about. No. Okay. what happened up here to this, where did this inhomogeneity, the cosmic microwave background themselves came about. And today, the leading scenario, by no means fully established, but still leading scenario, is inflation. And what it says is that if you begin early enough, then the universe could have been exactly homogeneous and isotropic, except for the quantum fluctuations, which by Heisenberg uncertainty principle, you can never switch off. So there are these vacuum fluctuations, which you could never switch on just because of quantum mechanics. And these vacuum fluctuations can grow to form the cosmic perturbations we see in the cosmic microwave background, which then, under gravitational influence, produce a large-scale structure. So the origin of the universe, observed large-scale vacuum structure, is the origin of the observed large-scale structure can be traced back to vacuum fluctuations. It's really a very beautiful story of cosmogenesis up here. So basically, what happens is that here we got quantum fluctuations going into inhomogeneities, and these inhomogeneities growing, and therefore the origin of the cosmic structure that we see is really quantum nothingness, the quantum vacuum, the fluctuation in the quantum vacuum. Now there is another paradigm shift, and it has to do with the new meaning of the Big Bang. And this is a documentary. There's a small YouTube video with several leading cosmologists, Hawking and Penrose in particular. And they talk about what the current belief of Big Bang is. The current belief is that Big Bang really refers not to an initial singularity, but only to hot phase of the early universe, say at the end of inflation. So I think I urge students to see it. It's very short. It's only a few minutes, like 6.5 minutes. And so you can see that and for yourself. And there's also just published a monograph that students and also other faculty might be interested in. It is called The Origin of Space-Time Physics. It collects the seminal papers by these people, which really by Lorentz, Poincaré, Einstein, Minkowski, and Friedman and Lemaitre, which says how our current picture of the universe has come about. Okay. So I have spoken for about 45 minutes. Should I go to the last talk, which is last part, which is very small? Is that okay, or shall I stop?
Yes, Professor.
Okay.
The time is yours.
All right. So this is the last part, which has to do with the ripple with gravitational waves. So this is also a paradigm shift, which is, I think, surprising, and a lot of this history people don't completely know. As you know, since 1915, for the last 5 years, gravitational waves have made a huge impact on physics as a whole, and astronomy as well, and it is in news all the time. And this is thanks to these LIGO detectors we have seen that there are these gravitational waves, and these gravitational waves are messengers of the most violent events in the universe. For example, black hole collisions and neutron star collisions. The black hole collisions are telling us a lot about how dynamics of galaxies and so on in the early universe, how black holes could be formed of the observed masses and so on. And also collision of neutron stars is teaching us a lot about nuclear physics and even quantum chromodynamics. We start really in 1916, a year after Einstein published a general relativity paper. In this epoch-marking paper, he also realized that just as time-changing electric dipole produces electromagnetic waves, X-rays, visible light, infrared radio waves, in the weak field limit of general relativity, Einstein did not work with full general relativity, but just weak field limit, so linearized gravity on Minkowski space background, time-changing quadrupole moment produces gravitational waves. So if I have a mass which is not spherical but has some quadrupole moment, and if it is oscillating, or if I have a binary system of two stars and which is going around, then it's like a rod with like a dumbbell with a rod with two heavy weights up here, and if it's going around, then the quadrupole moment is changing, and this change of quadrupole moment gives rise to gravitational waves. And that's what we're seeing with black holes going around each other, binary black holes, or neutron stars going around each other, and we see these gravitational waves detected in the LIGO detector. But again, today we all think, oh, of course, there are gravitational waves. But it took the longest time for people to accept. even though the first paper came in 1916, surprisingly, Einstein himself caused confusion about whether gravitational waves exist in full nonlinear general relativity or if they're artifacts of the weak field approximation that Einstein himself made in 1916. So what was this confusion? Einstein had then a younger Nathan as an assistant. This is his picture when he was much older. And Einstein, together with Nathan, did some piece of work. And in a letter to Max Born, he wrote in 1936 that this piece of work, which I'll explain in a minute, showed the following. Together with a young collaborator, Nathan Rosen, I arrived at the interesting result that gravitational waves do not exist in exact general relativity, though they had been assumed to be certainty in the first approximation. And then he goes on to say, this shows that nonlinear gravitational wave field equations, the full set of Einstein's equations, tell us more, or rather limit us more than we had believed before. In the linearized approximation, the gravitational waves, Einstein is saying, but he is claiming that in the full nonlinear theory, field gravitational waves do not exist. It's a shocking story up here, and historically it's even more interesting, because Einstein and Rosen sent this paper to Physical Review, and the title was, Do Gravitational Waves Exist? Arguing that they don't exist in full nonlinear general relativity. But the paper, Einstein submitted 3 papers to Physical Review in 1936. This one, and then there was a paper of Einstein-Rosen bridge, and then the famous paper of Einstein-Rosen Podolsky paradox, Einstein-Podolsky-Rosen paradox, or not? It's not a paradox; it's a fact, right? I mean, and the other 2 papers were actually published without a referee report. But this, because Einstein seemed to contradict himself, that gravitational waves don't exist. The paper was sent to a referee, and it went to Robertson of the Robertson-Walker Universe, cosmologist. He was on sabbatical at Caltech from Princeton. Einstein was at Princeton, but Robertson was on sabbatical in Caltech. And Robertson read the paper and wrote an 8-page report and showed that although the conclusion was okay, the calculation was okay, the conclusion was wrong, because what Einstein thought was a singularity was really a coordinate singularity, and that could be removed by coordinate transformation. Einstein was angrily withdrew the paper from Physical Review and said that he doesn't agree with the conclusion. But then he submitted it to the Franklin Institute. But between the time it appeared, it was submitted and it appeared, Einstein realized that, in fact, that was right, that there was a coordinate singularity and it could be removed. And therefore, in fact, what there was perfectly nice solution of Einstein's equation, full nonlinear equation, showing that there are gravitational waves which are cylindrically symmetric, somewhat artificial approximation. You need to have a cylindrical object, infinite cylinder in full, which is changing quadrupole moment, and that would actually emit gravitational wave. But that the title was changed, and it was really on gravitational waves instead of do gravitational waves exist. And the abstract says a rigorous solution of cylindrical gravitational waves is given. So Einstein changed the paper in the proofs. And Nathan, by the way, continued to believe the original conclusion that gravitational waves do not exist well into the 80s. So I'm saying all this thing not to sort of, paint these very thoughtful, very esteemed, and very original physicists in a unfavorable light. That's not what I'm trying to do at all. But in fact, I'm trying to say that, well, look, these people are great people. They have done such marvelous discoveries. They have such insights, but even they can make mistakes. And therefore, the paradigm shifts occur when people have courage to swim against the prevailing paradigms. So the resolution of the confusion came to the work of Hermann Bonji and his group, and Roger Penrose, Ted Newman, and other people working with Roger. And the reality of gravitational waves in full nonlinear general relativity was firmly established only in the 1960s through systematic theoretical analysis by these people. On the observational side, it was established by careful observations by Russell Hulse and Joe Taylor of a binary pulsar system, and that led to a Nobel Prize in 1993. They observed it again for a very long period of time, and then through this very careful observation, they deduced that the pulsar was actually, the binary pulsar was actually losing mass exactly as predicted by the quadruple formula of Einstein's, and therefore gravitational waves exist. But they did not see the gravitational waves. Rather, they just saw the effect of the gravitational waves on the orbits of the per pulsar. The pulsars were falling closer towards each other because they were losing energy through gravitational waves. Tiny amount of energy, but with these 20 years of observations, one could actually conclude that gravitational waves exist, but indirectly. And the direct, so one might ask, why such indirect methods of detection? Could we not just set up a laboratory to see gravitational waves? Well, the gravitational waves are ripples in the space-time geometry. And space-time geometry, it turns out, is extremely rigid. You know, if you have some object like rubber, and if I squeeze it, then there is a stress and a strain following the Young's law. And that's the stress is proportional to, the stress is proportional to the strain, right? So the contraction of the rubber will be proportional to the stress that is applied to it. Same thing will be true even with steel, but steel has a huge Young's modulus. That's why it is so difficult to compress steel. It turns out that space, geometry of space-time, has even larger Young's modulus. It is about 10 to the 25 times that of rubber and 10 to the 22 times that of steel. And that is, so although steel is 1,000 times more rigid, if you like, than rubber, the space-time geometry is 10 to the 22 times more rigid than steel. And therefore, only extremely violent events can shake space-time geometry sufficiently to create effects that are observable. But such events do occur, and therefore, as I said, the direct observation of gravitational waves and the discovery of black hole and neutron star collision in this last 5 years has led to gravitational astronomy. We have got detailed images that we cannot obtain from electromagnetic waves, detailed images of this violent phenomena, and we have a new brand window on the universe. Previously, most of our knowledge of the universe came through electromagnetic waves. Now we are also learning through neutrinos, but in the last 5 years, we have learned much more about the universe through gravitational waves than other windows. In other words, we have really made a huge progress, which we could not have made just with the electromagnetic window. And this is the first detection on Earth, and this really is a triumph of human ingenuity, because you need technology, incredible technology. These laser interferometric detectors, if you like, they are able to they are able to detect tiny length changes in the separation of the mirrors, and this is really tiny. I mean, it is really like it's a 4-kilometer long interferometer up here, and then one is actually seeing the changes in the mirror position, and those changes are, or of the size of the proton or size of elementary particles. And one can have such ingenuity to create these instruments, and then theoretical ingenuity to be able to calculate the waveforms exactly and then compare with them observation. And the first event was very loud, and luckily it occurred the very first day that detector was turned on. And then I said 4, this is old transparency, but now there are about 24 subsequent black hole mergers. And there's one definitely binary neutron star merger, which was followed by about 70 electromagnetic observations, and it has resolved decades-long mystery about short, hard gamma ray bursts that they really occur because of collision of neutron stars. In this collision, by the way, heavy elements are copiously produced. One did not know how heavy elements like uranium and plutonium and gold could be produced in the universe, and they are produced copiously here. People estimate that something like 2 Earth masses of gold was produced in this hard event that took place. So this really brings me to summary. I talked about general relativity, which brought about paradigm shift, then black holes, then Big Bang and gravitational waves. Each time there is a paradigm shift that occurs. So what are the lessons that we have? Let me see. The lessons that we have are the following. First, what is now considered as common knowledge, the same slide I had before, was not at all so just a few decades ago. In fact, most of the scientific community at the time was thinking in almost the opposite direction. Secondly, precisely because they are so startling at first, the dramatic paradigm shift takes decades to get settled and become the new common pool of knowledge. And third, the factors driving or slowing the process are varied. It's not a matter simply of logical steps, as is made to appear in retrospect. And finally, there is a sense of balance. And to me, this is my own life. I learned this as the most deepest lesson of doing science. You should take the standard paradigms with a grain of salt, but you should pursue what you believe. On the other hand, each time you obtain results, so here is optimistic, you're saying that what you believe goes against the standard paradigm, but we should still continue to work it out. But once you have the result, this is the hard part, you obtain the result, you really have to re-examine them. You have to be your own worst critic and see if in fact they stand this criticism. Otherwise, you can fool yourself and just, there are a lot of people who say everything is wrong, Einstein is wrong, this is wrong, etc. And they have no real argument. So one has to be very, very careful. One has to have courage to say that maybe Einstein is wrong. But then when you find the reason for which Einstein is wrong, you have to be very, very critical and see that it really is the case. And so there was this summary of everything I said here is really in these three paradigm shifts. It is captured, very well captured by this famous biologist. And he talks about what happened in the second half of 20th century. The physicists succeeded magnificently, but in doing so, revealed the limitation of human intuition. Unaided by mathematics and understanding of nature, they discovered comes hard. The cost of scientific advance is the humbling recognition that reality is not construed to be easily grasped by human mind. We are used to certain scales, and if you go to subatomic scales, or if you go to the large scales of the universe, things that can happen there cannot be extrapolated from our experience, which happens on human scale. And the paradigm shifts illustrate audacity of human race to see, to go beyond, to imagine, and to pursue things that go way beyond what is directly pursued. But then once you have seen such, once you have gone beyond and obtained as a result, then you have to have this sense of balance that I mentioned. Thank you.
Thank you, Professor Abhay Ashtekar. We have some questions, but before we proceed, I would like to ask everybody to turn on their microphones for a huge round of applause in retribution. It's good to have this round of applause, because then you change a bit the feeling that you're talking to an empty room, and to realize that instead of it, you've been talking to more than 150 people, both collecting together the people that are in this virtual room and in the YouTube. Before we proceed to the questions, Professor, please allow me to give you an overview of the audience that you had. I would like to start telling you that we had many, many people from all around Brazil, from all the 5 Brazilian regions. That Brazil is huge, as you know. So from the north here in Pará, obviously, where I'm speaking from, northeast, like Bahia, Maranhão, Paraíba, Pernambuco, Piauí, Rio Grande do Norte. This is the name of the states. In the center-west region, we have from Distrito Federal, the capital of Brazil, and Tocantins. From southeast, Espírito Santo, Minas Gerais, Rio de Janeiro, São Paulo, and also from the deep south in Brazil, in Rio Grande do Sul. So obviously, we have our students from our graduate program, our undergrad students, postdocs, teachers, professors, like Caio Macedo, Jorge Castanheiras, Carolina Benoni, people from all around the Pará states that is by itself big, not only the capital, Belém, but also from the surroundings and also far away cities like Salinas and Santarém. We have not only just people from physics, but also from other related areas like geophysics. We have here Cicero Regis, but we have also students, postdocs, teachers, and professors from Brazilian universities, institutes, research centers, and observatories. If you allow me, I perhaps should mention some of them, like Álvaro Nogueira from Cefet Rio de Janeiro, Daniel Vanzella from USP São Carlos, Gabriel Menezes from Federal Rural do Rio de Janeiro, Gustavo Lanfranchi, São Paulo, Hugo Capelato do INPE, Ion Vancea, Júlio Fabres, Marcos Maia from Brasília, Maurício Calvão, FRJ, Matheus Lobo, Nelson Studa, Nivaldo Lemos, Paulo Piva, Satis Kuma Vieira, Saulo Carneiro, Vitor Afonso from Campina Grande, and a lot of other people, most of them close friends. And let me tell you that we do not have only a Brazilian audience. We have also audience from different continents, right? So we have, for instance, Antonio Pereira Jr., that I believe it's attending us from Netherlands. We have Eloy Ayon Beato. I don't know if he's from he's attending from Mexico or Cuba, but we have Isaac Ramirez from Mexico. We have Miguel Tovar from Colombia. We have Miquel Miravet from Valencia in Spain. And we have, if I understood correctly, Ritik Roy from Fudan University in China. So as you see, many people, it's a bit late in China or early.
Yeah, it's 3 o'clock in the morning.
Okay, so let's now jump to the questions. So the first question has been registered from Satish Kumar VH, that is also from India. So Satish, would you like to make the question, please?
Thank you, Luis. Thank you, Professor Ashtekar, for the talk. Nice historical insights. And it's a pleasure, great pleasure to see you in Brazil, although virtually. Especially thank you for clarifying the popular misconception about black holes in Newtonian gravity, right? My question is, we have something called universal horizon, and of course, your own inventions like discoveries like isolated horizon and dynamical horizons, right? So can we define any of those things in Newtonian gravity?
No.
That's my first question.
No, so none of them are defined in Newtonian gravity just because of the speed of light being relative. I mean, here the whole idea about light being trapped, for example, in the isolated horizons, you have got expansion of null rays, and expansions of null rays are, it vanishes on the isolated horizon. It's negative on one side, positive on the other side. This cannot happen in Newtonian gravity. So in Newtonian gravity, we do not have any of these horizons because the speed of light is not absolute; is relative.
And speed of light does not enjoy any privileges in Newtonian gravity.
Right, so. And it's infinity.
Thank you. The second and the last question is, I think you modestly left out the fourth paradigm shift, which involves you. So could you please tell us, like when you reformulated general relativity in terms of the new variables, right? So right. Now we know it's part of the upbringing of a formation of a theoretical physicist. But I've never heard you talk about how well it was received when you first introduced these things. Thank you.
When I first introduced it, in the circles of general relativity, it was received very well. I mean, people like Penrose and Newman and even George Ellis and so on, they were very interested in looking at this. In some ways, one is looking at general relativity upside down because the metric becomes a derived quantity, secondary variable quantity, and the parallel transport of fermions becomes the primary quantity, and yet we can recover all of general relativity. Roger Penrose, as you know, has the Twister program, and he was trying to do something similar in a way. And in fact, I was very, very motivated by Roger's ideas on twistors. I was a postdoc in Oxford before I did this work. So I was really deeply influenced on that. But in the twisted language, one always is even today, one does not really know how to do real general relativity. One is always doing self-dual or anti-self-dual, which are complex sectors of general relativity. It's very beautiful work, and we have learned a lot in these sectors, but it's not real general relativity. So because I could do the real general relativity using those ideas which people had, it was very well received in the general relativity circles. In the particle physics circles, it was not so well received because they kind of felt that, and for a long time they felt that strongly, that general relativity was just a force and somehow it can be treated by perturbative quantum field theory or something more, and that there's no reason to look at general relativity by itself or gravity by itself. You could look at it as a unification and then it will be automatically taken care of. So there was a kind of quite a bit of division between how it was received. It's not that they were not interested. I mean, Witten, for example, did refer to this paper when he did his 2+1 gravity, saying that, well, what he was doing in 2+1 dimensions was done in 3+1 dimensions in this paper that I had written, and so on and so forth. But as a general idea that this is something that is important that may lead to quantum gravity was not something that was appreciated by or well received or taken seriously in the particle physics circles, but it was taken very seriously in the general relativity circles.
Thank you so much for the answer.
Sure.
Okay, thank you, Satish, for your question. Thank you, Professor Ashtekar, for your answers. The next question comes from Matheus Lobo from Federal University of Tocantins in the center of Brazil. Matheus, do you want to make the question yourself?
Yes, sure. I can read my question. Can you hear me?
Yes.
Yes, please.
Okay, thank you very much for your talk. It's a great honor to meet you in this meeting. My name is Matheus Lobo. I'm a theoretical physicist and a pure mathematician. I have two questions. First, do you think there's a chance regarding the paradigm shift you mentioned? Do you think there's a chance that there's actually no space-time inside the event's horizon of a black hole, meaning all matter and energy lie in its surface? The motivation for this lack of space-time in the interior of a black hole is due to two things. Probably space-time supports at most the Planck density of energy and matter, causing a rupture in the fabric of space-time if this limit is exceeded. And the second reason for the motivation is that the entropy depends solely on its surface area. The second question is related to the first, and if this hollow...
So what was the first question? I understood your statements, but what was the first question?
Yeah, the first question is, do you think there's a chance that there is actually no space-time inside the black hole, meaning all matter and energy lie in its surface?
Okay.
Okay, and the second question is that if this hollow black hole theory is correct, do you think should it explain dark matter's gravity actually without the need of dark matter particles itself?
Okay, so the first question, I think it is not really possible that everything is just on the surface. And the point is that people have tried to construct such detailed model that is really everything is just lying on the surface up here. But then what would happen is that if light ray is actually coming out and incident on such matter, then it would heat up this matter, if you like. I mean, energy falling, it would heat up more matter, and we'll be able to see the surface. We'll be able to see light coming out of these surfaces. And there are very detailed calculations done by the Harvard group, which was led by Ramesh Narayan, for example, in which they did this astrophysical analysis. And in fact, that's how they wanted to say that something is a black hole. This was before LIGO, that something is a black hole. And it is basically because you don't see a signal that you should have seen had there been no black hole. And so there should be this echo. There should be some things which are reflected that we do not see. And the second thing is about dark matter being, can it be explained by black holes? I think I'm not expert in the sense that I have not followed this work in technical detail, but the general consensus is that you cannot explain all dark matter with black holes. There can be a fraction of dark matter, a small fraction of dark matter with black holes. And there is also work going on in saying that there can be small black holes, much smaller than the Chandrasekhar limit, much smaller than one smallest solar mass, so to say. And people are sort of saying that these black holes could have been formed from dark matter itself. And but these are speculative ideas, but people are pursuing them. But I think it's not possible. The observational bounds which say that you cannot have more than a small fraction of the dark matter in the form of black holes. And these are all very detailed studies from observation from astrophysicists.
Okay, thank you very much.
Thank you, Mateus, for your questions. Thank you, Professor Ashtekar, for your answers. So the next question comes from the YouTube, comes from, just a moment. Yes, comes from Francisco Lustosa, that is from the Brazilian Center for Physics Research. Does Professor Ashtekar have a preferred view on the possible solutions to the singularity problem? Could it be avoided by quantum effects, for instance? I want to know your opinion.
Right. So, the answer is at 3 levels, right? The first is that in general relativity, we say that there are singularities because it is a fact that curvature actually diverges. Space-time curvature diverges there. And that's not a coordinate effect. You can actually calculate curvature scalars and they become infinite. I mean, the Schwarzschild singularity, the Riemann tensor square is a curvature scalar, is coordinate independent, and that becomes infinite. But one can ask the following question at the classical level, even at the classical level: can we actually reformulate Einstein's equations in such a way that under normal conditions, the new equations, so to say, can we generalize, if you like, slightly generalize Einstein's equation, so that under normal conditions, the equations are completely equivalent to Einstein's equation. But these equations, the newer equations, they won't have a metric as a basic variable because the metric becomes bad there. But there's some other basic variable so that we can actually evolve across the singularity. And then once we are on the other side of the singularity, you can convert again everything back into the metric variables. So it's a funny question to ask, but this question can be answered using this spinorial or the connection variables that I had found. And those, it is actually surprising, but for cosmological singularities and for the Schwarzschild black hole singularity or space-like singularities, you can actually evolve. In other words, you replace Einstein's equation with some other equations which are equivalent to Einstein's equation if the metric is invertible. But if the metric fails to be invertible, the new equations are still valued. You can still do evolution. And so from that point of view, one can say that, well, some of the singularities see some mathematical variables or some physical observables, but is blind to other physical observables. And we can do the evolution. The other physical observables to which it is blind are sufficient for us to do actually evolution across the singularity. So even in classical theory, without quantum theory, the singularities, there are singularities in the sense that curvature blows up or metric becomes bad, but we can replace these with some other variables which are equivalent under normal conditions, and then they don't break down. So the notion of singularity depends on which questions you ask. For some questions, you can have a well-defined evolution in classical general relativity, but not for all questions. Then we can ask the question at the level of quantum field theory in curved space-time. And in quantum field theory in curved space-time, what you have is that, again, for these singularities, cosmological and the black hole singularities, it turns out that if you think of the quantum field as a really observable, I mean, only quantum observables, not classical observables, then in fact, the field observable itself can be evolved across the singularity. It doesn't see the singularity, classical singularity at all. If you have a probe, which is quantum field, that quantum field can evolve across the singularity. But if you construct certain observables, like, for example, if you have a field phi, you can construct a renormalized field phi squared. And surprisingly, that also doesn't see singularity. But if you construct more complicated field observables, like the stress energy tensor, then it sees. So the statement is that at the first level, the number of observables which see singularity is large, and there are only exceptional ones which don't see singularity, yet enough for us to do the evolution across the singularity. At the second level of quantum field theory in curved space-time, the number of observables which don't see singularity is large, but still not large enough, because stress energy tensor, quantum stress energy tensor, is actually an observable, and it does see the singularities. And now, therefore, a third level, which is what about pure quantum gravity? And I think that loop quantum gravity has shown, which is based on these connection variables, that the space-like singularities are naturally resolved. The strong space curvature singularities are naturally resolved in loop quantum gravity. So if you bring into account loop quantum gravity, it means that what happens is really at the singularities or near the singularities in the Planck regime, you cannot use the space-time continuum in the usual sense of the word. You have to replace it with a quantum mechanical state of the geometry. Geometry is a physical entity, and just like matter, matter is described by wave functions in quantum mechanics. So geometry should also be described in terms of wave functions. And if you describe it in terms of wave functions, then the statement is that the evolution does not break down, everything is perfectly fine. And so I think that it is the case that once one has a satisfactory quantum theory of gravity, one would see that all general relativity singularities are naturally resolved. There is no singularity at all, but that our notion of Einstein's continuum breaks down there. We have to replace it by a genuinely quantum mechanical state and do the evolution. In loop quantum gravity, we see that this happening with space-like singularities, but we don't see this happening with the time-like singularities or null singularities, and that is an open question. But my expectation is definitely that the satisfactory quantum theory of gravity would not have any singularities.
So thank you, Francisco Lustosa, for your question. Thank you very much, Professor Abhay Ashtekar, for your answer. And the next question comes from this room, Luca Abraão, that he's from Cefet in Rio de Janeiro. Luca, do you want to turn on your microphone and make the question yourself?
Yeah, sure. Thank you so much for the talk, Professor. It's been a pleasure to virtually meet you, I guess. So I was thinking, if you think that the divergency between the new calculations of the cosmological constant becomes the sort of a new paradigm shift in general relativity and cosmology.
I lost something.
Sorry.
Then I lost you. Do you think what?
Yeah, I've heard that there was some divergence between the calculations of the cosmological constant. Do you think that this could be a new paradigm shift in general relativity and cosmology?
Yeah. So the statement is that would there be a? Yeah. I mean, okay, good. So statement is that we do have a cosmological constant, as I was telling you before. To me, it was very amusing how there's a very clear discussion. I mean, again, time is limited, so I could not have all the quotes up here. But there's very clear discussion that took place. Actually, they were walking after a Solvay conference in a garden in Brussels, where Einstein and Lemaitre were talking, and Lemaitre told Einstein that, well, whether there is a cosmological constant is an observational question, and one should not decide it just because you don't like it, because it looks ugly or something like that. And then, as we know, I mean, Lemaitre is right that there is a small cosmological constant. So one of the questions that is really is that, in some sense, it is there, but it is very small compared to other quantities of nature, other fundamental constants of nature or something. And the answer is I completely agree. But for a while, it is now not fashionable, but for a while, when with Feynman and these people, that generation of people, they are very concerned, Dirac too, very concerned about why is Newton's constant so small. Now, what does that mean? That means that if I take a proton and an electron, and I calculate, or two electrons, if you like, and I calculate the Newtonian attraction between them with respect to the mass, where the constant G appears, and if I calculate the electromagnetic force between them, or the repulsion between them due to the electric charge, then we get a factor of 10 to the 40. In other words, Newton's constant, if you like, is about the strength of gravitational interaction, or Newton's constant, is about 10 to the minus 40 times the electromagnetic constant, alpha. And so the people are concerned about this, saying, why is this the case, and so on and so forth. And so today's question about cosmological constant is very similar. I mean, it is very puzzling why it is so small compared to other things, but not zero. And my answer is the following, that indeed, if there is a natural mechanism which explains some grander theory, which explains that why Newton's constant is so small, or also why cosmological constant is so small, it will be a big breakthrough. There's no question. It will be a paradigm shift. It will be because you will be explaining what we today believe the constant of nature. It's a bit like what happened with the Bohr atom of hydrogen atom, right? Before Bohr atom, Rydberg's constant was a fundamental constant of nature. But with Bohr's model of hydrogen atom, Rydberg's constant could be expressed as a formula in terms of the mass and the charge of the electron and h bar. One needs h bar. So one could be, which could just explain so one constant disappeared, and of course, this theory of hydrogen atom was a paradigm shift. So I'm sure the same thing will happen. If we have a theory which explains smallness of cosmological constant, it would be a paradigm shift. But on the other hand, I want to say that people like to say is a problem, namely the cosmological constant is so small. I don't consider this to be a problem, to the same extent that I don't consider it to be a problem that Newton's constant is very small. I mean, it is very small, but we calculate with it. So similarly here, it's a parameter, we take it into account and calculate with it. It's a parameter that goes in Einstein's equations, and we just work with it. So the short answer is, yes, if one can explain the smallness of the cosmological constant by some really natural, without putting something behind, mechanism, it would be a paradigm shift. It will, on the other hand, it is not something that prevents us from making progress today. Even if we don't understand why it is so small, we can make progress today, just like we make progress all the time, even though Newton's constant is very small.
Okay, thank you very much.
Thank you, Luca, for your question. Thank you, Professor Ashtekar, for your answer. So the next question comes from YouTube, Diego Renan. I don't know where he's speaking from. He wrote, after the detection of gravitational waves in 2018, after the detection of gravitational waves, what is the future perspective of this research area, in your opinion?
Well, I think the future perspectives are huge, and it's an exciting area. The point about gravitational waves detection, of course, the first detection was direct detection was very, very important. But as I was mentioning in the talk, what we have is really new window on the universe, right? Which we did not. Okay, I guess I don't have it. It's a new window. Yeah, no, I do have it here. It says here we have a brand new window on the universe. So it's like, it's really like that phenomena which were invisible to us because we did not have this window. If like we did not have the right glasses to see this particular thing, and suddenly we see all kinds of things happening in the universe which we had no idea were happening before. So it's really enriching our understanding of the universe very, very much. As I was saying, to me, it's very exciting that in fact, even with QCD, which is called quantum chromodynamics, theory of strong interactions, one is probing these interactions usually through particle accelerators in CERN. But that can sort of understand, one can understand through that what is happening at kind of high temperatures, whereas with neutron stars, the relative temperature is low, and there are also transitions, quark-gluon, transitions that take place, and those we cannot learn from nuclear physics. Those are nuclear physics, but we cannot learn them from laboratory experiments or accelerator experiments, and we can hope to learn them through gravitational waves. And there's very active research, very detailed calculations that if one observes this, then the equation of state will be this. If the transition between the confined phase of QCD and unconfined phase of QCD will be governed by this particular equation of state, or will have this description. If we, on the other hand, we don't observe it, then it will have some other description. So we're learning through gravitational waves even about, elementary particle physics, which to me is very beautiful. It's very, very powerful. And this is now, people, funding agencies in the United States who are normally fund Department of Energy, for example, who normally would fund nuclear physics and studies of elementary particles, want to now fund gravitational waves for this reason. I'm just giving you one example. There are many examples in astronomy that people are learning about. New things are happening. For example, this whole idea about how are the heavy elements created, right? By heavy, I mean heavier than iron. Because stars, are created up to iron because of nuclear reaction, but then one reaches a saturation point. A few heavier elements could be created with small abundances, but not too much. And when I was a graduate student, we are always told, this great insight of Fred Hoyle's, that this is what these heavier elements are created in supernova explosions. And we all know, until 5 years ago, that's what I believed. And I told people that, the heavy, we are here, for example, the heavy elements, or gold is here, or platinum is here, is because of these things that are spewed out in the supernova explosion. But now it seems more and more, really, almost completely convincing, that no, the real mechanism, the more powerful mechanism, is the collision of these neutron stars. So we suddenly understand where gold comes from, where platinum comes from in the universe. And to me, these are kind of really understanding of phenomena which have been mysterious to us for a long time, in nothing to do with gravity directly, but we are getting information about them through gravitational waves. So to me, this is really exciting. It has a huge potential. And now the statement is that currently the idea is that they are going to upgrade the current detectors that we have in the United States, the LIGO detectors. They will go into, they'll be upgraded. But then in there is international collaboration which is searching to create the third generation gravitational wave detection, which will be, for example, the interferometric arms currently are 4 kilometers, but then there'll be 40 kilometers, and there are committees which are working on, the science case, what is the best thing to do, what is the cost for something. And there is a project in Europe called Einstein Telescope, and there's a project in the United States called Cosmic Explorer, and both these projects are going ahead. The planning for them is going ahead. They're going to be expensive, but there's great excitement. So funding agencies are exploring ways for international collaboration to make this possible. So I think the future is extremely bright. If I were a young person, I would definitely work in gravitational waves. And I still work in gravitational waves, but I work on more mathematical aspects of it, whereas I would work on other aspects like nuclear physics or phenomenology.
Okay, so thank you very much, Hannah, for your question. And Professor, I think people, they are not going to stop making questions, because every time they make a question, you give us so rich and interesting answer that it's very, very nice to hear from you. But let's move on. We still have questions here. This one comes from Ritik Roy. I believe he's in the room, and I believe he's speaking from China. Ritik, do you want to make the question yourself?
Hello, can you hear me?
Yeah.
Thank you for the talk. And my question is a bit general, and I think you already answered it in a way, but I just wanted to ask what your thoughts are on how the new paradigm shift in gravitational physics has come from, or like which field in gravitational physics the new paradigm shift is going to come from. Yes.
Yeah, so I think partly, as you said, there's the gravitational wave physics itself, but also there are the issues of quantum gravity, right? I mean, the issues about whether the Planck scale phenomena are manifest in the early universe. To me, that is a real possibility. I mean, the last papers I have written have to do with that, for example. That's a real possibility. And so I think we might actually have a paradigm shift coming from applications of quantum gravity to the early universe. The same thing is, I mean, conceptual paradigm shift could also come from, you know, a really definitive answer to the information loss issue. I don't call it a paradox because there is no paradox. I think, you know, the question is, well, how does the information, what happens when the black hole evaporates? Can you understand it fully? And that, I think, has a potential of changing saying that some of our currently cherished ideas are incorrect. And so, to me, there is a potential also at these fundamental levels that there could be a paradigm shift. And these paradigm shifts, both in cosmology and in this black holes, they may have, just like general relativity had, they may have effects, they may have ripples on other areas of physics as well. And as I already mentioned, gravitational wave physics itself is already having ripples in other areas. And so that is likely to create also a paradigm shift. I think that, yeah, so these are the examples that I would give.
Okay.
Thank you for the answer.
Thank you, Roy, for your
Are you in
question.
China, really?
No, I'm actually in India because
Okay.
I couldn't travel because of the COVID. Yeah.
Yeah, but even then, I guess it's still very late for you. So
Yeah,
very
it's
nice
like
of you.
1:15.
Good.
Okay. So thank you, Roy, and thank you, Professor Ashtekar. So we have some comments. One from Mauricio Calvão says, extremely beautiful and brilliant talk with very stimulating conclusions and recommendations. Thank you a lot. And Carlos Chico Lustosa makes another question. He says, from YouTube, he says, what are your thoughts about the current status of cosmological constants as dark energy, besides the aesthetical and experimental arguments? How could we explain its fundamental origin? I know you already commented about that, but do you want to further comment on?
So, I mean, one possibility is really that, I don't have a good answer for that. I mean, that's if in fact, as I said, if in fact we have really a fundamental explanation of this, why there is a cosmological constant, but not really very small, it will be really, really good. I kind of feel that if we understood quantum gravity much better, and ideas associated with the renormalization group flow might actually show that the cosmological constant is not zero, but very small. But I mean, the preliminary papers that I've written on this, but I think we're still far from that. So my short answer is that something like, you know, renormalization group flows, or some aspect of quantum gravity, which are really genuinely non-perturbative, might actually come to help us and explain why this cosmological constant is very small. But as I said, you know, Newton's constant is also very small, and somehow, you know, in the 50s and 60s, people like Feynman were quite bothered about it. Dirac wrote, you know, all kinds of papers on this, relating it to, you know, some cosmological parameters, you know, the number of protons in the universe and such things. So people were bothered about it, but then they stopped. For some reason, they stopped being bothered about it. And so if you were to ask me from 20 years from now, I think it's most likely scenario is that we would not have the answer, but people will just get used to the fact that cosmological constant is small. It's a fact of nature. But if in fact somebody does have an answer, it would be a true paradigm shift.
Okay, thank you, Lustosa, once again. Thank you, Professor Ashtekar. So we have other comments. So Gabriel Menezes says, wonderful talk. Saulo Carneiro from Federal University of Bahia says, thank you, Professor. Gabriel Menezes talking from Rio de Janeiro. So, Professor, we are almost achieving 2 hours. So let me do the following. I know there are further questions, but let us now let room for a final question in which you could also give your final remarks, and then we close this wonderful afternoon in Brazil, right, with your webinar. So the last talks, in fact, different people that ask you about that. So one of them is in YouTube, and is Luis Raul Betancourt. Can you please comment on loop quantum gravity? And as I said, so if you want to make this round up, I mean, this closure, I mean, we will be very grateful for that.
Yeah. Okay. So loop quantum gravity is very much in the spirit of general relativity, in which one takes this Einstein's idea that geometry is a physical entity, just like matter, very, very seriously. And the point is that we all know that matter has atomic structure. And if geometry is a physical entity like matter, then therefore it should also have some microstructure. And the question is really, what are the building blocks, or figuratively atoms of geometry? That is the idea. And loop quantum gravity provides one answer to that. It doesn't mean that it is the final answer, it's the correct answer or something, but it's an attractive answer as to what exactly is the nature of the building blocks of space-time geometry. And the fundamental excitations of space-time geometry in loop quantum gravity are one-dimensional. And the idea is that when we think about a classical continuum, then we've got many, many of these one-dimensional excitations. And the favorite example I like to give is really that you just look at your shirt, right? It looks like a two-dimensional continuum, smooth one, completely nice, but you just have to take a magnifying glass and see that it's actually woven by one-dimensional threads. So your shirt is really a one-dimensional object. It's just that it is crisscrossed by one-dimensional threads, and therefore, for all practical purposes, it has a two-dimensional appearance. In loop quantum gravity, the same thing is true with space itself. If you like, the fabric of space is woven by one-dimensional threads, which are these Wilson lines, if you like, of the connection that I had found. So we got this description, which is on the one hand is giving us a detailed picture of the microscopic geometry of space-time in terms of these one-dimensional excitations. So the idea is that if you take a surface, like for example, I don't know if you see this pad of paper up here, then it has some area. And the idea is that, well, that area in loop quantum gravity is attributed to the surface because actually the microscopic structure of geometry is such that there are many, many one-dimensional excitations, and they all intersect this surface, and they deposit a quantum of area. And the quantum of area is minuscule, it's Planck length squared. So it is 10 to the minus 66 centimeters, if you like. So it's really minuscule. But then you've got so many intersections that for all practical purposes, it looks like a smooth continuum. It's just like the laser light. It looks like a classical Maxwell field, but we know it has many, many, many photons, which are all superposed coherently. And the same thing is true with this born up, with the way that the space-time geometry is born. And then finally, this picture actually breaks down in the extreme situations. This fabric, if you like, of the space actually tears near the singularity once you reach the Planck regime. And then you cannot describe it in terms of the continuum picture. It's a bit like if you take a water, and the water you can explain in the continuum picture. But if you heat it, then the vapor comes out, and then you really have to have molecular dynamics of H2O, right? And then you can do thermodynamics of vapor. So similarly here, the statement is that we have to take the building blocks of this space-time much more seriously in the Planck regime. And that is why one can actually resolve the Big Bang singularity or other cosmological singularities because one can replace the continuum with these building blocks. And the building blocks, nothing, I mean, they don't diverge. Nothing is wrong with the building blocks. It is the insistence that there should be a continuum space-time picture. That is what is not right. So loop quantum gravity has made a lot of progress, particularly in cosmology and also in black hole physics. But on the other hand, we are still quite far from the final loop quantum gravity theory. In other words, what we have done is we've taken sectors of general relativity, which have sufficient symmetries, like in cosmology or black holes, and then we understand them very well, applied the loop quantum gravity ideas to these sectors, and then we can understand them very well, and that is what we have been successful with. But without any symmetries on the general thing, it's not that we don't have formalism, but it doesn't completely fit together yet. It doesn't completely give you a coherent picture from which everything could be derived. It's not impossible that this will be happening at all. I mean, younger people are actually working on this. There's progress ongoing, but I don't want to say that, oh, it's clear that it's all going to be finished in the next 3 years or something. No, I think the questions we are struggling with are hard questions. There is a steady progress that is happening, but I think it's not that we're going to have the full theory of quantum gravity, which has no problems at all. That is not in the immediate future. But as I said, right, continuous advances are being made.
Okay, thank you, Professor. So I know I said it was a last question, but well, I mean, maybe I'll do an exception for a very close friend of mine, Daniel Vanzella from São Paulo. So he's asking, string theory has been a promise of paradigm shift for about 4 decades now. What is your take on it? I'm sorry to.
No. I don't have any problems at all. Thank you. Okay. Yeah. So I think it is indeed, and at times people had even said that string theory would be theory of everything. How it was from, and I have even heard people saying that it's going to explain everything, including human behavior and how poetry is born. And I would say that that promise has not been fulfilled at all. And I had this, I mean, for the first, until about 2008 or something like that, I was writing, I followed string theory, and I would write my annual notes on string theory every year, just to say where we are. And after that, I stopped because the main kind of progress in string theory was not really on quantum gravity issues anymore. It was mainly because of the Maldacena ADS-CFT conjecture. The whole thing shifted from understanding gravity, quantum nature of gravity, to applying gravity to solve problems in other areas, which is, of course, by itself important and good, and there's no question about it, in particular for QCD, for fluid dynamics, and so on. Right? So we haven't seen really any decisive program on the long-standing problems of quantum gravity, like the nature of time, what happens to the Big Bang, singularity. Can we sort of talk about predictions of the in for CMB from the cosmological space-times, which are unambiguous. Even the basic building blocks of string theory, which are really that space-time is higher dimensional, that one needs that. One needs a negative cosmological constant at a fundamental level. And because we've got space-time which is higher dimensional, there's a huge tower of particles. And finally, supersymmetry is essential, so supersymmetry should be there. None of these things have had any experimental verification at all. And so I had my own views about this, but I was pleasantly surprised that the string theories themselves are agreeing with this view. Namely, there is actually a very nice article which you can find on the website of the Institute for Advanced Study. It is written by a science journalist, but she was a journalist in residence there, and she interviewed the local experts in string theory, who are the leaders in string theory. And the conclusion is, and in fact, even the title of the article, was that string theory has not lived up to its promise of unifying quantum theory and gravity or general relativity. And in the beginning, it looked like there will be some simple equations that will come from string theory, from which the rest of the physics will follow. In other words, it will provide us a unified theory of everything. And this hope is far from being realized, has not really realized at all. But more importantly, what has happened is that there is now a second rebirth of string theory. And that rebirth is not string theory, which gives us the unified theory of all nature, but a theory that provides us an extremely rich toolbox, which will be useful in completely diverse areas of physics. So it's the second life of string theory is as an extremely rich toolbox. And and it is true. I mean, from number theory in mathematics to QCD to hydrodynamics, one can use ideas of string theory. but it is not string or even superconductivity, room temperature superconductivity. But none of the really hardcore room temperature superconductivity is explained. But it enables us to calculate some Green's functions, which is very, very important, which because in strong coupling limit one, we could not calculate those Green's functions before. So string theory has provided us unprecedented, very rich toolboxes, a toolkit. And I think that is the, I mean, not me, but the article was saying that, and therefore I agree with that, that the current and in the near future or foreseeable future role of string theory is that it is a very rich set of toolbox. Okay, that's all I wanted to say about.
Okay, okay, Professor. So, well,
I'm not demeaning it, by the way. I mean, that's valuable, but that's not solving problems of unification of general relativity and quantum theory.
Okay, you know, I must tell you that we are still more than 100 people that are attending to you, but it's a pity. But I think we have now passed the 2-hour limit, and I think that's time to close. Many people write it in the chats, and Júlio Fabris from Espírito Santo, professor from Federal University of Espírito Santo, says, thank you very much for your webinar, and many compliments and thank you messages. So to close it up, Professor, I would like to
make a closing statement before you.
Okay, please go ahead.
I just wanted to say that it is a real great pleasure for me to be with you all today. And I've been to Rio and I've been to Sao Paulo, and I've firsthand witnessed the vastness of the country and its culture. And I know that really very, very good work is being done all across Brazil. And so in a way, it's ironical. But, you know, if it had been normal time, I would have just gone to Amazonia and given my talk there. And that talk would have been well received by the local people. And I would have spent many more hours discussing with students and answering their questions. But in a way, ironically, this very difficult situation has made it possible for all of us to get together, and for me to share my ideas and for you to ask me questions. So I'm really very, very happy that I could do this and that you all came and participated in this. So thank you very much.
Professor, we thank you. I think your final words, just said everything. That's the spirit. So we know the pandemics is a tragedy, but out of the tragedy, moments like this teaches a lot for us of what will be our future from now on. So, Professor, thank you very much. And I'll ask everybody to turn on their microphones once again for a final round of applause in retribution for this excellent afternoon that we spent together.